In the last video, we talked about identifying infinite limits based off of a graph. And we saw that whenever a function was increasing or decreasing without bound, the limit as x approached a was equal to either positive or negative infinity. That was our definition of an infinite limit, and that often correlated to having a vertical asymptote as well. In this video, we talk about finding infinite limits algebraically. Infinite limits occur as x approaches some real number a if direct substitution yields a non-zero number in the numerator and 0 in the denominator. So we're going to have some sort of fraction, and direct substitution gives us a non-zero number in the numerator and a 0 in the denominator. Now, why does this give us positive or negative infinity? Well, remember, when we say limit, we're talking about approaching an x value. That means that our denominator is approaching 0. It's getting closer and closer and closer to 0. So technically, it's not equal to 0, but it is infinitely close to 0. And dividing by an infinitely small number is the same as multiplying by an infinitely large number. All right, that is very important to recognize. Dividing by an infinitely small number is the same as multiplying by an infinitely large number. Think if you were to divide by 1/10. Well, dividing by 1/10, that is the same as multiplying by 10. Dividing by 1/100th, that is the same as multiplying by 100. Dividing by 1/1000th is the same as multiplying by 1,000. So dividing by an infinitely small number is the same as multiplying by an infinitely large number. Here are steps for evaluating infinite limits algebraically. Step number 1, use direct substitution. And we've said before, always start off with direct substitution. Use direct substitution to confirm the existence of an infinite limit. Okay, notice you'll have a non-zero number in the numerator and 0 in the denominator. And correspondingly, a vertical asymptote at x equals a. All right, if you have an infinite limit as x approaches a, x equals a is going to be a vertical asymptote. If this is the case, we move to step 2 and we can factor the denominator. Use the factors and direct substitution in the factored form to determine the sign of the denominator. Pay careful attention to the zeros, all right? You'll see that coming up. We have to determine whether or not the zeros are going to be a positive 0 or a negative 0. Interesting. 3, use the sign of the numerator and denominator to determine whether or not the quotient will result in positive infinity or in negative infinity. All right, so these are our 3 steps to finding infinite limits algebraically. Again, direct substitution gives us a non-zero number in the numerator divided by 0 in the denominator. We know that our answer has to be positive or negative infinity. It's our job to figure out which one. So, evaluate the following limit analytically. Verify your results with a graphing calculator. We have the limit as x approaches 3 from the left of 2 divided by x squared minus x minus 6. Well, again, anytime we go to evaluate a limit, we want to start off by trying direct substitution. And when we plug in 3 for x, we get 2 divided by 0. Notice we get a non-zero numerator and 0 in the denominator. And that tells us we are dealing with an infinite limit. Our answer has to be positive infinity or negative infinity. Let's see if we can't figure it out. The next step is to factor the denominator. In this case, our denominator factors into x minus 3 times x plus 2. Now we can think about our direct substitution in the factored form. Notice, we are approaching 3 from the left. Well, if I plug in a number that is ever so slightly less than 3, right? As I'm approaching 3 from the left, I can think of that as being like 2.9999999999999. If I plug in 2.999999999 in for x, I essentially get 0, but it is going to be negative, right? If I have a number that's just ever so slightly less than 3 and I subtract 3, I'm going to get a negative 0. In this factor, when I plug in 3, I get out 5. So this gives me 2 divided by a negative 0 and by negative 0, I mean a number that's infinitely close to 0 but negative, times 5. Well, let's continue with our algebra. 0 times any number is going to give us a 0, but because this is a negative times a positive, we end up with a negative 0 in the denominator. And 2 divided by a negative 0, this is 2 divided by an infinitely small negative number. Again, dividing by an infinitely small negative number is the same as multiplying by an infinitely large negative number. That gives us a positive, and over a negative gives us a negative infinity, comma, dne for our answer. Let's look at the limit as x approaches 3 from the right. Well, again, our direct substitution, we still get 2 over 0. That tells us we're dealing with an infinite limit. The answer has to be positive or negative infinity. Let's figure it out by factoring our denominator. Same denominator here, same numerator, and let's think about our direct substitution in this case. Here we are plugging in a number that is ever so slightly greater than 3. I am to the right of 3, approaching 3 from the right. So something like 3.00000000001. And if I plug that in for x, this factor will essentially become 0, but it will be positive. It's going to be some number that's infinitely close to 0, but positive, a positive 0. If I plug in 3 here, I get 5. This gives me 2 divided by a positive 0 times a positive 5. Well, in my denominator, a positive times a positive is a positive. We're going to get a 2 divided by a positive 0. And now I have a positive divided by a positive. Well, that's going to give me a positive solution, which has to be positive infinity. Again, dividing by an infinitely small positive number is the same as multiplying by an infinitely large positive number. That results in infinity. And we also write dne. So there are our left and our right-sided limits. Now we can evaluate the general limit, the limit as x approaches 3 of 2 divided by x squared minus x minus 6. Well, because the limit from the left is negative infinity and the limit from the right is positive infinity, we simply say the limit as x approaches 3 does not exist. And we could verify this on our graph. Here we have x equals 3. Notice as we come from the left of 3, the graph goes down to negative infinity. As we come from the right of 3, the graph goes up to positive infinity. And once again, we have the presence of a vertical asymptote at x equals 3. Let's look at another one. Evaluate the following limit analytically. Verify your results with a graphing calculator. So in this case, we have the limit as x approaches 2 from the left. Again, we always start off by trying direct substitution. 2 squared is 4 minus 8 plus 3. Well, 4 minus 8 is a negative 4 plus 3 gives me a negative 1. I plug in 2 into the denominator. I get 0 squared. I get negative 1 divided by 0. Negative 1 divided by 0. I have a non-zero number divided by 0. That tells me I am dealing with an infinite limit. The answer will either be positive infinity or negative infinity. To find out, we must factor the denominator. And in this case, we just have x minus 2 times x minus 2. That's x minus 2 quantity squared. And let's now think about what happens with our direct substitution. Well, in the numerator, we plug in 2, and we get out negative 1. That's going to give me a negative 1 in the numerator. In the denominator, I'm plugging in 2, so each of these factors is going to turn into a 0. However, we need to determine whether or not they're going to be a positive 0 or a negative 0. If we are approaching 2 from the left, that means we are ever so slightly less than 2. And if I have a number that is just slightly less than 2, say 1.99999999999, and I subtract 2, I'm going to get a number that's infinitely close to 0, but negative. All right, this is going to be a negative 0, and same thing with this factor here when I do my substitution, a negative 0. Negative 1 divided by negative 0 times negative 0. Well, let's simplify now. Negative 0 times negative 0. A negative times a negative, that gives me a positive. I have a negative 1 divided by a positive 0. Negative 1 divided by a positive. Negative over a positive gives us a negative infinity, comma, dne for our answer. Let's now look at the limit as x approaches 2 from the right. Again, we try our direct substitution. When we plug in 2, we get negative 1 divided by 0. That tells us we have an infinite limit. What do we need to do next? Factor the denominator and look at the signs of our factors, in particular the ones that are going to be zeros. Well, when we plug in 2 into the numerator, we're still going to get out negative 1 in our numerator. But now in the denominator, let's think. We're plugging in a number that is to the right of 2, just by the tiniest amount. It's infinitely close to 2, but just slightly greater than 2. If I plug in a number that's just slightly greater than 2 and I subtract 2, I'm going to get a number that's essentially 0, but positive. A positive 0 here and a positive 0 here. That gives me a negative 1 divided by a positive 0 times a positive 0. Positive times a positive, that gives me a positive in my denominator. Negative 1 divided by positive 0, a negative divided by a positive, well, that gives me a negative. Negative infinity is our answer. And now that we have evaluated both the left and the right side limits of 2, we can evaluate the general limit, the limit as x approaches 2 of x squared minus 4x plus 3 divided by x minus 2 quantity squared. Well, the left and the right limits were both negative infinity. If the left and right limits equal each other, then that is our answer for the general limit. Negative infinity, comma, d and e. And again, we can verify our results graphically. We can graph our function. And we notice that as our x values get closer and closer to 2 from the left, the y values go down to negative infinity. Same as we come from the right, our x values get closer and closer to 2 from the right, the y values go down to negative infinity. And again, the graph confirms that we do indeed have a vertical asymptote at x equals 2. All right, so that is how we evaluate infinite limits algebraically.